The traditional estimation method of the mean takes into account this fact. We use probability theory in a different way. So in previous lectures we saw probability theory, and in probability theory we start with a given distribution, in this case a normal distribution, which, as I said many times, this is similar to considering a population of values, and based on that we determine what is the probability of observing a specific value of the random variable, a specific value of y. Okay, the probability for each value is given by this curve, which is a normal distribution. That's easy to do. That's probability theory. And the probability daemon very easily provides that information for us. Now, estimation is more complicated. It's quite difficult to do. So now we go the other way. Given observations, which is samples that we collect, represented here by the white dots, we make an estimation of the distribution or population of values that this sample comes from. And we want to know mainly one of the parameters of that distribution. We typically assume that the distribution is normal in this case, but that's not necessarily the case. And we want to know what's the mean of that distribution. And sometimes we are also interested in the standard deviation of that distribution, but we almost always are interested in the mean of the distribution. So this is something that we don't know, and we are going to estimate from the data. We are going to use the services of the probability daemon to do that. Okay, so before I explain the estimation, I'm going to make a digression. I like to direct your attention to different types of distributions. So remember that in terms of discrete distributions, we saw the Bernoulli distribution, and the Bernoulli distribution gives us the probability of one success in one trial. If we expand to more than one trial, then the binomial distribution, it's in a sense a summary of Bernoulli distributions. So if we have more than one trial, we can apply the one Bernoulli distribution for each of the trials to determine what's the probability of success in each of the trials. But it's a bit cumbersome to use so many Bernoulli distributions. So instead of that, we use a binomial distribution, which is an expansion of the Bernoulli distribution. And the binomial distribution will tell us not what's the probability of a success in each of the repetitions of the trial, but what's the probability of having a okay number of successes in n trials. So for example, if the number of trials is 4, okay, the binomial distribution will tell us what's the probability of observing, if k equals 0 is 0 successes. If k equals 1, what's the probability of observing 1 success? If k equals 2, what's the probability of observing 2 successes? And if k equals 3, what's the probability of observing 3 successes? And I said n equals 4, so I have to say k equals 4. What's the probability of observing 4 successes? So in one distribution, we've got a summary of 4 Bernoulli distributions. Okay, so that was in terms of discrete variables, but we typically use continuous variables, or not typically, but we use a lot continuous variables in psychology, and continuous variables we cannot use Bernoulli and binomial. Instead, we use a normal distribution. That's the most popular of the distributions. And I want you to show you, because this is quite is not as clear as in the case of the discrete, that we use the Bernoulli for one trial and the binomial for a summary of several trials. We can do the same in continuous. The problem is that we use the same distribution for both, and that's what makes the understanding of this concept difficult. Okay, so we've seen before, so for one trial, we determine the probability of observing a specific value of the random variable using a normal distribution. That's what I've just shown in before. Now, if we extend the number of trials, then we can do two things. First thing is to use, for each trial of we determine the probability of observing specific value using a normal distribution. So if we have 10 trials or 10 observations of y, then we have to use 10 normal distributions to establish what's the probability of observing each of the possible values. Instead of doing that, we can take a summary. So instead of using being interested in the probability of observing one value of y, we take a sample of values of y and we calculate the mean of those values. And now what we are interested in is not in each observation of y, but we are interested in the mean of y. And we express the mean with this line on top of the y. So this is a different type of normal distribution. Well, in terms of the structure of the distribution, the distribution is normal, so it's the same. But instead of taking values of random variable y, it takes values of the mean of y. Okay, so now after this digression, let's see what the probability daemon does to help us make an estimation of the population. Okay, so the probability daemon will do the estimation based on information we provide. It somehow simulates what we did and repeats it thousands of times. And the outcome of what the probability daemon does is a sampling distribution. Okay, so we have to provide to the probability daemon a summary of our sample. So we obtain a sample of values and that y takes, and that's represented by each of these white dots. And we calculate the mean equals 50 and the standard deviation 20. The n is the number of observations, which is 30. We provide that information to the probability daemon. And what do we want? We want mu, which is the mean of the population. So this sample we obtained comes from a large population. So we want to estimate what's the mean of that population. The probability daemon will give us as I said, a sampling distribution, and it will give us the mu hat. What's mu hat? So this hat indicates estimation. So it will give us an estimation of mu. Because we don't know mu, because we don't have access to the large population we are interested in, we are going to get a mu hat, which is an estimate of mu. And that sampling distribution will be a normal distribution. And that normal distribution, remember, the values are, we can determine where the 95% of the values are, and I should say central values, so center around the mean of that distribution, are located. And these will give us what we call the confidence interval. Okay, so the process starts with the probability. First step, the probability daemon assumes that mu equals the mean of the sample. Okay, so the mean, estimating the mean is quite easy, because what's the best estimation of mu, which is the mean of the population where our sample comes from? Well, exactly the mean of our sample. What about sigma? What about our estimation of the standard distribution, of the standard deviation of the population of values? Well, it is also the standard deviation of our sample. Okay, now the probability daemon assumes also that the population of values, these population of values resembles a normal distribution. So now we are going to have a normal distribution with mean of mu and standard deviation of sigma. Okay, but that's not it, because we want to know the confidence interval. We want to know how good is our estimation. Is it quite precise that the value of the mean of our sample is exactly the same as the mean of the population? Well, obviously this is not true, because the value that we obtain in our sample has some, it has to be related to the exact mean of the population, but because it was randomly chosen from the population, then it's not going to be exactly the same. It has to be different. And we determine the precision of our estimation with the 95% confidence interval. Okay, so how do we obtain the 95% confidence interval? That's more complicated. That starts with step 2, which the probability daemon obtains a random sample of 30 values. Why? Why 30 values? Well, because that's what we did. And remember that somehow the probability daemon is doing what we've done. We obtain a sample of 30 values. So that's what it does. And then it calculates the mean of that sample, which is what we did as well. We calculated the mean. Now, once it did that, it will repeat the process thousands of times. So the repetition of the process starts first with returning those 30 values to the pool of the population of values, and obtains a new random sample of 30 values, and it calculates, step 5, calculates the mean of that sample again, and it repeats the process 10,000 times. It can repeat it, actually. The probability daemon comes from the Laplace's daemon, and it can do immediately something that is infinite. So we stop at 10,000 because that we humans is something that we can process, but the probability doing can do even longer. And actually with 10,000 repetitions, it's good enough for what we want. Now, the probability daemon now has 10,000 means by doing that process. And now it generates a distribution of those means. So let's see the process here in graphs. Okay, so we start with the data. We went through this already. And we obtain the mean and the standard deviation in our sample. We, by assumption, we ask the probability daemon to work for us. We make an assumption that the mean of that distribution, the mean of the population is exactly the same as the mean of our sample. We made the assumption that sigma, the standard deviation of that population, is the same as that of our sample. And we made the assumption that the distribution is normal in the population. And finally, we get a sampling distribution made by the probability daemon. Sampling distribution of the mean. So it generated from this distribution that is assumed, the probability daemon obtained 10,000 samples and calculated the mean of that sample 10,000 times. So this is the distribution of means, not of samples of 30 observations, not distribution of values, raw values of y. It's distribution of means of y. And as you can see, it also follows a normal distribution. It's not an assumption anymore. There is a proof that determines this. So if we start with this distribution and we do what this probability daemon did, we end up with this distribution. What characteristics has? The mean of this distribution is exactly the same as the mean of the assumed mean of the population and the mean of the sample. And the sigma, or rather than the sigma, the standard error of the mean, SEM, standard error of the mean, is the standard deviation of this sampling distribution. As you can see, this distribution is much more narrower than the distribution of the population. So the standard error of the mean, which is the standard deviation of this standard distribution, sampling distribution of the mean, is given by this formula, which is sigma over the square root of n. And n in this case is 30 because it's the sample size. And we estimate this using the sample of the standard deviation of our sample, like this. And I must say that we typically, instead of using the normal distribution, we use the t distribution, with the degrees of freedom n minus 1, so 29 in this case. Now, what do we do with that distribution? Well, remember that in a normal distribution, we have 95% of the values between the value minus 1.96 and plus 1.96. We have in this interval, we've got 95% of the values. So basically what we do is to the full estimation, it comprises the estimate of the mean of the population, which is exactly the same as the mean of our sample. And then we've got the confidence interval. The way we calculate the confidence interval is by first identifying the lower bound of the interval by doing negative 1.96 times the standard error of the mean, and we add the mean of that distribution, which is the mean of the sample and the assumed mean of the population. And then the upper bound of that interval is 1.96 times the standard error of the mean plus the mean of the sampling distribution of the mean.